So let's take a look at sketching some of these angles in what we call standard position. Standard position is the position of the angle that starts at 0 degrees. Okay, and so it always starts on what our graph would look like, the x-axis. Okay, it starts in that standard position. So we're going 42 degrees. Well, 45 degrees is going to get us right at about here, about halfway. And so if I want to go 42 degrees, I'm going to go a little less than halfway. And in order to finish that off, I need to label it. I want to say that it's actually 42 degrees there. Okay. Now, obviously, this is just a sketch. Okay, so it's not the whole angle. It's just a sketch. You can make a better sketch if you wanted to do this on some sort of a computer software, but I'm looking for just an idea that you know how to do these angles. The next one is negative 113. So if you notice on 42 degrees, we went counterclockwise up and to the left from the standard position, the 0. The negative 113, I have the same idea with the graph. And I'm going to start here at the x-axis at the 0 points, but I'm going to go negative 113. Well, negative 113 means I'm going to go down this way. So this is negative 90. And negative 113 is going to be somewhere in here. If I go halfway, then that's negative 90 plus 45, which is 130. Okay, so I'm not quite halfway. When I draw in this angle, I want it to be a little bit less than halfway. Let me move that so it's even a little bit closer here. Okay. So I've got roughly negative 113 degrees. Okay, so that's going in a clockwise direction as opposed to a counterclockwise direction. And you notice I put a little arrow on the end so that you know which direction we're actually going with this. 4 pi over 3. So 4 pi over 3 is in radians. So pi over 3 is at the 60 degree mark. So the 60 degree mark, I'm going 60 degrees plus another 60 degrees plus another 60 degrees. I'm at 4 sets of those 60 degrees. And so for me to be looking at graphing this, I've got 60 degrees, which gets me to here. Another 60 degrees gets me to 120. Another 60 degrees, which is 3 pi over 3, would get me to just pi, which is 180. And then I'm going another 60 degrees, which gets me down here, slightly over halfway. And then I can draw this line in. And I'll move it over here. So I've got 180 is going to be 3 pi over 3. And I'm going to go 1 pi over 3 past that, or an extra 60 degrees past that. And this is going to be 4 pi over 3. Now, D is an interesting one. D has negative 4.6. Okay, so automatically, most people think, oh, well, I'm going to go in the negative direction, which is good. And I'm going to go not extremely far away from the origin or the x-axis, the 0 point. And that's not necessarily true because negative 4.6 is not in degrees, it's in radians. And the way that I know it's in radians is that there's no angle measurement. There's no degree on the upper right-hand side. Okay, so I know that this negative 4.6 is in radians with a pi version. And so when I think about making this graph, I want to think more about the decimal version than I do about the pies or the pies over 3s and pies over 6s, things like that. I want to think about how far do I have to go in order to get to negative 4.6 radians. But I do know that I'm going in the negative direction, so that's good. And if I think about it, I go all the way over here. If I made that angle, that's negative 3.14. That's negative pi. Okay, negative 3.14. Well, this is negative 4.6. So then the question is, do I keep going farther than the next line, or am I shorter than that next line? And so what I want to do is I want to pull up a calculator to take a look at that. And if I pull up that calculator, I've got negative pi, and then my next one is going again a negative pi over 2, so I'm at negative 3 pi over 2. And so if I take that negative 3 times pi, which is 3.14, and then I divide that by 2, that's negative 3 pi over 2 is 4.71, negative 4.71. Well, that's too far. I only need to go negative 4.6. And so I'm only going to go here, to about here. And again, hopefully with your pencil and paper you can draw this a little bit better. I just want to bring this a little bit closer so that it's on a little bit. And you can see that it's not touching that line. It's not didn't go all the way there. And again, my smortboard's off a little bit here, but we can try to grab it with a mouse and get it to match up. There we go. So that's about negative 4.6. Negative 4.71 would be the negative 3 pi over 2. And so I don't want to go that far. I only have 4.6, negative 4.6. But I have more than negative pi, because negative pi is 3.14. So this over here was negative 3.14. This is negative 4.71. Okay, so I need to be somewhere in between those, and a lot closer to the negative 4.71 than the negative 3.14. So this should be a good sketch of what your graph should look like then. And then the last one here, 420 degrees. So 420 degrees, I'm going in the positive direction. If I go here, I'm at 90, 180, 270, 360. Okay, and I need to go 420. So 360, if I go all the way to the next 90, 360 plus 90, it gets me to 450. So 450 is too far. And so I end up about here at 420. So that angle is 420 degrees. I went all the way around the circle, 360, and I went an extra 60 degrees, which is a little past halfway, but not quite to the 90 degrees. So that's sketching an angle in standard position. Let's move on this sheet then. For some reason my thing's not sliding, but we finally got it here. Find the angle in radians that satisfies the conditions below. A radius of 7 and an arc length of 3. Well, in order to do that, we need a formula for arc length. And the formula for arc length is S equals R and then theta, the symbol with a 0 with a line through it. And the R is radius. the S stands for arc length, and the theta is the angle, except that that angle is in radians. Okay, so that's an important part, is that it has to be in radians. So I've got a radius of 7 and an arc length of 3. So I've got S equals R theta. This is R. This is S. So I've got 3 equals 7 times theta. So divide by 7. And theta is equal to 3 divided by 7, which we actually want to divide out here. 3 divided by 7 is 0.428714. Well, we'll do to the 10,000ths position. So there's theta. You need to know that that's actually in radians. Okay, that's the measurement. The next one, the radius of 4. So I've got a radius of 4 and an arc length of 13. Divide by 4. And theta is going to be 13 divided by 4. Which is going to get us 3.25. Notice that I didn't put a degree symbol on there. It is not 3.25 degrees. It is 3.25 radians. So if I don't put that measurement on there, then it's not it's not going to get me. It's not going to show that it's in degrees. It's going to show that it's in radians. Example 5: find the arc length of an arc on a circle with a radius of 24, intercepted by a central angle of 60. Okay. So we've got the central angle of 60, so I'm looking for arc length. So I'm looking for the arc length. It says find the length of the arc on the circle with a radius of 24 and a central angle of 60 degrees. Well, that 60 degrees is in degrees. Okay, so I need to change that 60 degrees into radians. So I do that by the work that we just did before. I multiply by 180 pi over 180 degrees, which gives me 60 pi over 180 because the degrees cancel out. And then 60 goes into 180 3 times, so I get pi over 3. So I'm actually multiplying this by pi over 3. And now that I have pi here, I can write my angle with pi. Multiplying these two together, I get 24 pi over 3. And 24 it can be divided by 3 8 times, so I end up with 8 pi. And that's how long the length of my circle is. Well, if you're not confident with 8 pi, you can do 8 times 3.14 if it makes more sense to you to have your arc length be 25.12. So it's pretty easy formula stuff. The next part is the area of a sector of a circle. Area of a sector of a circle. A is one area. We're looking at almost portions of triangles here. So we've got 1/2 the r squared times theta. Okay? And again, A is the area of the sector. R is equal to radius. And theta equals the angle. These are all central angles. So let me make a note of that. So the angle in radians again. Okay. Everything that we're going to be doing here is going to be in radians. So if it's not in radians, yeah, you need to convert it to radians. So when I look at example 6, I'm finding the area of the sector of the circle with a radius of 12. So just going to use the formula here. Area equals 1/2 radius squared theta with a radius of 12. An essential angle of pi over 3. Well, pi over 3 is already in radians, so that's good. Okay, we don't have to do any conversions here. So this is 1/2 times 144 times pi over 3. Half of 144 is 72. I can reduce, I get 72, let me do this first, 72 pi over 3. I can reduce 72 into 3. 3 goes into 7 2 times. 3 goes into 12 4 times. So 3 goes into 72 24 times. And you get 24 pi. Again, if you aren't comfortable with that being the area of a sector with pi's in there, you can go 24 times 3.14 is fine. I get 75.36. And either one of those are fine. Just like up here, either one of these were fine. Personally, I would prefer the 8 pi. It's a little bit more exact. There's no rounding that goes into it. But if you are more comfortable turning it into the decimal, go ahead and do that.